There is an element sitting quietly in the periodic table that managed to fool every scientist, every doctor, every engineer, and every miner who ever worked with it for roughly 400 years. Not because it was rare, not because it was hidden deep in some impossible corner of the earth. It was right there, in their hands, in their medicines, in their tools, and they still could not agree on what it actually was. And the one thing they were absolutely certain about, the one fact that made it into every textbook, every reference book, every chemistry course for over a century, turned out to be completely wrong. This element was supposed to be eternal, permanently stable, the last safe island before the periodic table tips into radioactive chaos. And then, not that long ago, a small group of physicists ran an experiment and quietly proved that the textbooks had been lying. Not on purpose, not through negligence. The universe had simply been keeping a secret, and the secret was this: nothing in existence is truly permanent. Some things just take longer to fall apart than others. This element takes longer than the universe has existed, but it still falls apart. Its name is not famous. You will not find it on a list of dangerous substances or celebrated discoveries. Most people have never thought about it for a single second, and yet right now, as you listen to this, it is almost certainly somewhere in your home, possibly in your medicine cabinet, possibly in the device you are using to hear these words, possibly in the fire safety system above your head. It has been embedded in human life for centuries, doing its work silently, without credit, without recognition, without anyone fully understanding what it was. That element is tin's heavier, stranger, more complicated cousin. It is the metal that expands when it should shrink, the metal that repels magnets when every other metal plays along. The metal that conducted science forward precisely because it was so bad at conducting electricity. And the metal that for 3 full centuries cured a disease without anyone knowing the disease existed. We are going to go through all of it, every layer, every contradiction, every moment where this element did something it was not supposed to be able to do. Because the story of this one substance turns out to be a map of how science actually works, which is nothing like how most of us were taught it works. It does not move in straight lines. It does not reward the obvious. It rewards the people who stop and ask why something that should not work keeps working anyway. So before we go any further, if this is the kind of story that makes you want to keep listening, do us a favor and subscribe, and leave a like. It genuinely helps this channel reach more people who love science told the right way. Now, let us go back to where this element actually came from. Not to a mine. Not to a laboratory. We need to go much further back than that. Picture 2 dead stars. Not dying, already dead. They burned through everything they had billions of years ago and collapsed into objects so dense that a single spoonful of their material would weigh more than every car ever manufactured on Earth combined. Now picture those 2 collapsed cores locked in orbit around each other, circling, pulling, drawing closer across a span of time so long it makes human history feel like a single breath. And then picture the moment they finally touch. What happens in those few seconds when 2 neutron stars collide is the most productive, violent event the universe knows how to make. The shock wave that tears outward is not just energy, it is a factory. In those seconds, conditions exist that cannot be replicated anywhere else in the cosmos. Temperatures and pressures so extreme that atomic nuclei begin capturing particles faster than they can respond, building heavier and heavier structures in a chain reaction that lasts only moments, but produces more heavy material than 1,000 ordinary stellar explosions combined. Gold comes out of this. Platinum comes out of this. And so does our element, forged in the collision of 2 stellar corpses in a galaxy that had no idea Earth would one day exist. When astronomers first detected the gravitational ripple from one of these collisions, a faint distortion in the fabric of space itself that traveled over 100 million light-years to reach our detectors, They immediately pointed every available telescope at the source. What they saw confirmed something that had been theorized but never directly witnessed. The flash of light from that collision carried the spectral fingerprints of freshly made heavy elements. The amount produced in those seconds exceeded the mass of our entire planet, in gold and platinum and bismuth alone. That material scattered into the surrounding space, drifted for millions of years through interstellar clouds, and eventually became part of the swirling disk of gas and dust that gravity slowly compressed into our solar system. Which means every atom of this element that has ever existed on Earth was already old when the sun first ignited. It arrived here as ancient cargo, embedded in the rock of a forming planet, waiting underground for something with hands to eventually come dig it up. And when those hands finally did, the first thing they did was mistake it for something else entirely. So this ancient material, forged in a stellar collision and buried in the Earth for billions of years, was finally found by human hands. And what did those hands do with it? They argued about it for 2 centuries straight. Not in a productive scientific way. In the kind of way where everyone is completely confident they are right, and everyone is wrong simultaneously. Miners in the mountain ranges of Central Europe kept pulling this metal out of the ground alongside silver and copper. And every time they tried to describe what it was, they ran into the same problem. It looked like lead. It weighed something like lead, but it melted differently, behaved differently in a forge, and left different residues when processed. Some called it a contaminated form of tin. Others insisted it was simply immature lead that had not finished forming underground. A few alchemists were convinced it was a transitional substance on its way to becoming silver, which tells you a lot about how alchemical thinking worked and very little about the metal itself. The name that stuck in German-speaking mining regions was something that roughly translated to white mine material, because miners are practical people and they named what they saw. A pale, slightly pinkish, heavy material that came out of the mountain with the silver and caused endless headaches during smelting because nobody could predict exactly how it would behave. What is remarkable is that a German scholar who spent years living and working in one of these mining towns actually wrote a detailed and largely accurate description of this metal in the 1500s. He described its weight, its melting behavior, its appearance, its tendency to appear alongside specific other metals. He got it mostly right, and science proceeded to ignore the practical implications of his work for another 200 years. Not because he was obscure, his books on mining and metallurgy were the most comprehensive reference works of his era. They were copied, translated, and distributed across Europe. People read them. They just did not connect the description on the page to the conclusion that this was a genuinely distinct substance worthy of its own classification. That is the part that gets me every time I think about it. The information was sitting there in print, available, readable, and the intellectual framework needed to act on it simply did not exist yet. Chemistry as a discipline, with real tools for distinguishing one substance from another, was still being invented. So the metal sat in a strange limbo for generations, used constantly, named inconsistently, understood by nobody. It was a French chemist working in the mid-1700s who finally ran the experiments that settled the question. He measured density, melting point, behavior in acid, reaction to heat. The differences from lead and tin were not subtle. They were obvious once you actually looked for them. He published his findings, and the scientific community slowly, reluctantly, accepted that this was its own thing. 200 years of practical use, then official recognition. That gap between doing something and understanding what you were doing turned out to be a theme with this element. It kept repeating, and nowhere did it repeat more strangely than in what happened next. Here is something that almost nobody thinks about when they consider how ideas spread across the world. Every book, every pamphlet, every scientific paper, every philosophical argument that traveled between cities in early modern Europe traveled on the back of a metal alloy. When the technology of movable type printing transformed how information moved, the people building the physical letters that pressed ink onto paper needed a very specific material. It had to melt at a manageable temperature so you could cast new letters quickly. It had to be hard enough to survive thousands of impressions without losing its shape. It had to flow smoothly into the fine details of a mold so the letters came out crisp and readable. And here is the one that eliminated most candidates immediately. It could not shrink when it cooled. Almost every metal shrinks as it solidifies. That is just what metals do. As atoms slow down and pack together, they take up slightly less space. For most applications, this barely matters. For a letter mold, it is a disaster. A letter that is even slightly smaller than its mold loses its sharp edges, and sharp edges are the entire point. The people who developed early printing alloys discovered through years of trial and error that adding a particular metal to the mix solved the shrinkage problem completely. That metal expanded slightly as it solidified, pushing the cooling alloy outward into every corner of the mold, producing letters with edges clean enough to cut paper. That metal was our element. The alloy that carried the works of astronomers proving the Earth moved around the sun, the writings of reformers that split the Christian church, the medical texts that began replacing superstition with observation. All of it was cast using a material that nobody had formally classified yet, that miners were still arguing about, that chemists had not yet agreed was its own substance. The most consequential information technology between the invention of writing and the internet ran partly on an element that science had not officially recognized. And the people operating those printing presses had no idea what they were working with, beyond the fact that it worked. They knew the recipe, they did not know the reason. Which is exactly the same situation that was playing out simultaneously in medicine, where this element was being handed to patients for problems nobody yet had the tools to properly diagnose. Every single property that makes this element useful is something that should, by normal logic, make it useless. Think about that for a second. We just talked about how it ended up in printing alloys because it expands when it solidifies. That is already backwards. But that is just the beginning of the list, and the further down the list you go, the stranger it gets. Start with the way it feels in your hand. If you have never held a piece of this metal, the first thing that surprises you is the weight. It is genuinely heavy, noticeably denser than iron. And yet the moment you apply any real pressure to it, it does not bend. It snaps. Clean. Like a mineral, like a ceramic, like something that has no business being classified as a metal at all. Copper bends. Lead crumples. Even relatively brittle metals will deform before they break. This one just fractures, and the fracture surface has a faint crystalline shimmer to it, almost like the inside of a geode. That brittleness comes from the way its atoms arrange themselves in a crystal structure that simply does not allow layers to slide past each other under pressure. Most metals owe their flexibility to exactly that sliding. Remove the ability to slide, and you get a metal that behaves more like stone than like steel. Then there is the melting point. 271 degrees Celsius. That sounds like a lot until you realize that iron melts at over 1,500, copper at over 1,000, and even lead, which we already established this element is heavier than, melts at 327. This metal melts first. You can melt it on a kitchen stove without any special equipment. When you mix it with certain other low-melting metals in specific proportions, the resulting alloy melts at temperatures so low that a cup of hot water is enough to liquefy it. That sounds like a curiosity until you realize it is exactly the property used in every fire suppression system installed in every public building you have ever walked into. The sprinkler heads above you in a shopping center, a hospital, a school, they are sealed with an alloy that melts at a precisely calibrated temperature. When a fire raises the air temperature to that threshold, the seal gives way and water flows. The whole system depends on a material that melts at exactly the right moment every time, without fail, after 30 years of hanging from a ceiling, doing nothing. And this element is what makes that precision possible. Because unlike many metals, it does not slowly change its composition or properties over time under normal conditions. It just sits there, waiting, stable, until the exact moment it is needed. Now the magnetic behavior, because this one genuinely surprised me when I first understood it properly. You know how a magnet attracts iron? That attraction is so familiar, it feels like a law of nature. Bring a magnet close to a piece of iron, and the iron moves toward it. This element does the opposite. Bring a powerful magnet close to it, and it is pushed away. Not because of some coating or treatment. That is just what it does, in its natural state, more strongly than any other metal known. The technical name for this is diamagnetism, and the reason it happens involves tiny currents that form inside the atoms when an external magnetic field arrives. Currents that generate their own opposing field. In most metals, this effect is so weak it disappears behind other magnetic behaviors. In this element, it dominates. With a strong enough magnet, you can make a piece of it float in midair. Just hang there, unsupported, pushed away from the field beneath it. It looks like a magic trick, and it is completely real physics. And then there is the electrical conductivity, which is where things get truly counterintuitive. That poor electrical conductivity, 30 times worse than copper, worse even than lead, turned out to be one of the most scientifically productive properties any material has ever had. And here is the part that the textbooks never quite explained with enough drama. For over a century, physicists studying how electricity and magnetism interact inside solid materials kept coming back to this element, not because it was good at conducting, but because it was bad enough that the subtle effects they were trying to measure were not buried under noise. When you run an experiment on a great conductor, the signal you are looking for gets drowned out by everything else happening. When you run the same experiment on a poor conductor, the signal stands out clearly. This element became the go-to material for some of the most important discoveries in the history of electromagnetism, not despite its weakness, but because of it. But none of that is what overturned the textbooks. None of that is the discovery that forced scientists to go back and rewrite what they thought they knew about the most fundamental nature of matter. That came later. And it came from a finding so unexpected that when the results were first confirmed, several senior physicists reportedly sat in silence for a long moment before anyone spoke. Here is what they found. For over 100 years, this element held a very specific and prestigious position in the periodic table. It was classified as the last absolutely stable element. Everything beyond it, every heavier element, was radioactive. It was not. That was the established, agreed upon, written into every textbook fact. And then a team of researchers set up an extraordinarily sensitive detector, cooled it to temperatures close to absolute zero to eliminate interference, loaded in a carefully measured sample, and waited. They were looking for a signal so faint that no previous instrument had ever been sensitive enough to detect it. They were looking for evidence that this supposedly eternal element was actually decaying. And they found it. Not a maybe, not a hint. A clean, reproducible, confirmed detection of radioactive decay. The element that was supposed to be the permanent endpoint of stability was not stable at all. It had been decaying the entire time, slowly releasing energy, slowly transforming into something else, right there in the reference books and the laboratory shelves and the pharmacy tablets, completely undetected for the entire history of human science. The half-life they measured was 19 quintillion years. That number is so large it is almost meaningless until you hold it next to something for comparison. The universe itself is roughly 14 billion years old. The half-life of this element is approximately 1,400,000,000 times longer than that. In the entire age of the universe, an almost immeasurably tiny fraction of its atoms have decayed. It is not dangerous. It will never be dangerous on any timescale that has relevance to human life, or even to the life of our planet. But the principle it destroyed was enormous. The idea that some matter is simply permanent, that some atomic nuclei sit outside the reach of decay, turned out to be wrong. There is no permanent. There is only slower and faster. And the question that immediately followed from this discovery was one that physicists had already been quietly wrestling with for decades. If even this element eventually decays, what about the particles inside the nucleus itself? Doctors were curing a disease for 300 years that officially did not exist yet. Let that land for a moment. Not treating symptoms, not managing discomfort, actually resolving the underlying problem in a large number of patients, repeatedly, reliably, across generations of medical practice, using a compound of this element, while having absolutely no idea what the problem actually was. The story of how that happened is one of the strangest collisions between practice and theory in the entire history of medicine. Go back to the early pharmacists who first started using bismuth compounds for stomach complaints. They had no germ theory. They had no concept of bacterial infection. They understood disease through frameworks that mixed observation with ideas about imbalance, bad air, and constitutional weakness. What they did have was the ability to notice that certain preparations worked and certain ones did not. And bismuth compounds worked. Patients with persistent stomach pain, inflammation, and the kind of deep, recurring discomfort that made eating a daily ordeal would take a preparation containing this element and get better. Not every time, not for every condition, but consistently enough that the practice spread and stuck across generations. Nobody asked why it worked. It worked, so they used it. Fast forward to the late 20th century. Two researchers in Australia, a physician and a pathologist working together, proposed something that the medical establishment initially found almost offensive. They argued that the majority of stomach ulcers were not caused by stress, not caused by diet, not caused by excess acid production, but by a specific bacterium living in the stomach lining. The idea was met with serious resistance. The stomach was considered too acidic for any bacterium to survive in. It was simply not a plausible environment for microbial life. The researchers gathered evidence. They published. They were largely dismissed. The physician then did something that I think about every time I hear someone talk about scientific courage. He drank a solution containing the bacterium himself, developed the expected inflammation, then treated it and recovered, documenting the entire process. That was the turning point. The medical community accepted the evidence. The bacterium was real. It colonized the stomach lining. It disrupted the protective barrier, and it was the primary cause of most ulcers that had been classified as chronic and essentially incurable for decades. Millions of people had been told their condition was manageable but permanent. It was neither. It was a bacterial infection that could be cleared, and the element that pharmacists had been prescribing for 3 centuries was effective precisely because its ions attack that bacterium directly. They disrupt the enzymes the bacterium needs to function, break down its outer membrane, and block the mechanism it uses to anchor itself to the stomach wall. All of that without causing meaningful harm to the surrounding human tissue, because the compounds involved are poorly absorbed into the bloodstream and pass through the body without accumulating. The practitioners of the 1600s were not guessing. They had found something real. They just could not see the mechanism because the mechanism was invisible to every tool available to them. 300 years of correct practice finally explained. And that explanation, when it arrived, immediately elevated this element from folk remedy to core component of the standard treatment protocol recommended by major health organizations worldwide. The gap between knowing something works and understanding why it works turned out to be 3 centuries wide. Which brings up a question that I find genuinely uncomfortable to sit with. If that gap existed for this long in medicine, where else does it exist right now? The answer, it turns out, is in physics laboratories. And the story there runs in the exact opposite direction. In medicine, practice ran 3 centuries ahead of theory. In physics, theory outpaced practice so completely that researchers spent decades building instruments sensitive enough to catch up with what the mathematics already predicted. We already talked about how this element became the primary experimental material for studying electromagnetic effects in the 19th and early 20th centuries. How its poor conductivity made subtle effects visible in a way that good conductors simply could not. But what came out of those experiments was not just a series of measurements. It was a window. The first clear window humans ever had into the quantum mechanical structure of metals. Here is what I mean. When physicists in the early 20th century began applying quantum theory to solid materials, they realized that electrons inside a metal do not move freely in every direction with every possible energy. They are constrained. They occupy specific energy states, and those states form a kind of 3-dimensional map in what physicists call momentum space. The shape of that map, called the Fermi surface, determines almost everything about how a metal behaves electrically, magnetically, and thermally. The problem was that for most metals, this map was essentially invisible. The effects that would allow you to read it were buried under too much noise at any achievable temperature. Then 2 Dutch physicists, working in a cold laboratory, surrounded by equipment that hummed and clicked and required constant manual adjustment, discovered something strange happening in this element specifically. When they varied the strength of a magnetic field applied to a sample, the magnetic response did not change smoothly. It oscillated. It went up and down in a periodic pattern, like a signal with a specific frequency. And that frequency carried encoded information about the shape of the electron energy map inside the metal. This was a quantum effect becoming visible in a macroscopic measurement. A property of individual electrons, entities so small they have no meaningful size, expressing itself as a measurable oscillation in a laboratory instrument. It worked on this element because it has relatively few electrons contributing to its conduction, which means the quantum effects are cleaner and more pronounced than in metals with crowded electron populations. Once physicists understood what they were seeing, the technique became one of the most powerful tools available for understanding any metal at all. You could apply a magnetic field, watch the oscillations, and read the internal electron structure of the material like a blueprint. And that blueprint turned out to be essential for everything that came after in the physics of materials, including the discovery that changed the entire conversation about what a solid material can even do. Because somewhere in the mathematics describing this element and its compounds, a prediction was hiding. A prediction so strange that when theorists first wrote it down, many experimentalists assumed it would never be demonstrated in a real material. It was a prediction about a new kind of quantum state of matter that nobody had ever seen, and that the usual rules of physics seemed to make nearly impossible. The prediction turned out to be correct, and the material that first confirmed it was, once again, a compound of element 83. The quantum state that theorists predicted and experimentalists confirmed in a bismuth compound is so strange that normal language barely fits around it. Imagine a material where the inside refuses to conduct electricity completely, like rubber or glass, but the surface conducts it perfectly, with almost no resistance, and does so in a way that is protected by the fundamental rules of quantum mechanics from any interference or disruption. Not protected the way a good insulator protects a wire, protected the way a mathematical law protects a logical conclusion. You cannot violate it without breaking the underlying physics of the universe. That is what a topological insulator does. The electrons on its surface move in specific directions depending on their quantum spin, and when they encounter an imperfection in the crystal, a missing atom, a contaminant, a defect of any kind, they do not scatter backward the way electrons normally would. They route around it and continue. The surface current is essentially immune to the kind of disruption that degrades every ordinary conductor over time and distance. When researchers first confirmed this behavior experimentally using bismuth selenide, a compound of our element, the result was not just a new data point. It was the opening of an entirely new chapter in materials science. Because sitting inside the mathematics describing topological insulators was a prediction about something even stranger. A type of particle, or more precisely, a type of collective behavior that mimics a particle, that had been theorized decades earlier and never observed anywhere in nature. The defining characteristic of this predicted entity is that it is its own mirror image. In particle physics, every particle has an antiparticle. When they meet, they annihilate. This predicted entity is both at once. It is its own antiparticle. And the reason physicists care so intensely about finding it is not abstract curiosity. It is because this property makes it extraordinarily resistant to the kind of quantum errors that are currently the single biggest obstacle to building functional quantum computers. A quantum computer stores information in quantum states that are almost impossibly fragile. Any vibration, any thermal fluctuation, any stray electromagnetic field can destroy the information before the calculation completes. Every major engineering effort in quantum computing right now is essentially a fight against this fragility. The topological approach offers a fundamentally different solution. If you can encode information in states built from these exotic entities, the information becomes protected by topology itself, by the mathematical shape of the quantum state, rather than by physical isolation. Errors that would destroy an ordinary quantum bit simply cannot reach a topological one. The geometry of the physics will not allow it. Research programs at major institutions and several large technology companies are actively working with bismuth-based compounds toward this goal right now, not as a distant theoretical possibility, as a near-term engineering target. A metal that medieval miners pulled out of the ground while arguing about whether it was lead now sits at the center of the most advanced computing research on the planet. And that is before we even get to space. The probes we have sent to the outer planets and beyond face a problem that no solar panel can solve. Past a certain distance from the sun, sunlight becomes too faint to generate useful power. Batteries run out. The only reliable long-term power source for a spacecraft traveling that far is the heat generated by radioactive decay, converted into electricity through a thermoelectric system. No moving parts, no fuel to run out, just continuous heat flowing through a material that turns a temperature difference into a voltage. The efficiency of that conversion depends almost entirely on the properties of the thermoelectric material. And the compound of our element that also turned out to be the first confirmed topological insulator, bismuth telluride, is still the most effective thermoelectric material known for the temperature ranges relevant to most engineering applications. It conducts electrons relatively well, but conducts heat poorly, which is exactly the paradoxical combination a thermoelectric needs. The heat flows through the electrons, but not through the atomic vibrations of the lattice, and that asymmetry is what generates the voltage. Every compact thermoelectric module used today in medical cooling equipment, in precision laboratory instruments, in the refrigeration units that do not use any moving parts or chemical refrigerants, contains this compound. And the next generation of deep space probes being designed right now will carry more efficient thermoelectric systems built around the same material, pushing power output higher and extending operational lifetimes further into the solar system than any previous mission. The same element is also inside the superconducting tapes that generate the magnetic fields in MRI machines, the machine that a doctor uses to look inside your body without any radiation, producing images of soft tissue with a clarity that would have seemed like science fiction a few decades ago, depends on a magnetic field so powerful it requires superconducting wire to generate without consuming enormous amounts of electricity. The tapes used to wind those magnets contain bismuth compounds processed into a flexible form, which was itself a major engineering achievement, because superconducting ceramics are normally as brittle as pottery. Getting this material into a form that could bend without cracking took years of materials science work. And those same tapes are being used in experimental fusion reactors, machines designed to confine plasma hot enough to trigger nuclear fusion using magnetic fields strong enough to contain a small artificial star. If fusion power ever becomes a practical energy source for human civilization, the magnets that make it possible will almost certainly contain this element. Now hold all of that together for a moment. A substance formed in the collision of dead stars, misidentified for 2 centuries by the people who mined it, embedded in the printing alloys that carried the ideas of the scientific revolution across Europe. Used in medicine for 300 years before anyone understood why it worked, classified as eternal, and then proved not to be. The go-to material for generations of physicists studying the quantum behavior of electrons. And now, sitting simultaneously at the frontier of quantum computing, deep space exploration, medical imaging, and fusion energy research. This is not a coincidence. This is what happens when a material has genuinely unusual properties. Unusual properties keep finding new applications because the universe keeps presenting new problems that those specific properties are suited to solve. The lesson here is not about bismuth specifically. The lesson is about what we overlook, the things that do not announce themselves loudly, that do not have obvious dramatic value, that sit quietly in the byproduct pile of some other industrial process. Those things have a way of turning out to matter more than the things we celebrated. We spent centuries mining this element as an accident, a bonus, something that showed up when we were looking for something else. And it turned out to be woven through the infrastructure of human knowledge and human survival more deeply than almost anything we actually went looking for. So here is the question I want to leave you with. If this element managed to hide its true importance for 400 years while sitting in plain sight in mines and pharmacies and printing shops, what else is sitting in plain sight right now that we are completely failing to see? What is the bismuth of our current moment? The thing we are stepping over every day on our way to something we think matters more? Write your answer in the comments. I genuinely want to know what you think. And if this story made you look at the world slightly differently than you did an hour ago, hit the like button and subscribe, because there are plenty more elements in that table, and every single one of them has a story just as strange as this one.